A machine so heavy it should collapse under its own weight. A walking factory that generates more power than 15 nuclear reactors combined. Legs the size of apartment buildings that somehow move across terrain. Engineers said was impossible. China just unveiled blueprints for a 52,000-ton mega machine that Western physicists called theoretical nonsense. But here's what nobody expected. They actually built it. And when it took its first steps across the Chinese desert, seismographs detected the footsteps from 30 kilometers away. Keep watching, because what you're about to discover might just change everything we thought we knew about engineering. Did you know that 70% of China's western expansion zones have no flat ground? Mountains, ravines, and unstable desert terrain have paralyzed infrastructure projects for decades. Traditional construction requires shipping materials piece by piece, assembling cranes that take 3 weeks to build, and building roads just to build more roads. The cost? Billions of dollars and sometimes decades of work for a single project. The 2008 Sichuan earthquake demonstrated this problem devastatingly. Infrastructure worth $150 billion was destroyed in minutes. Rebuilding took over 10 years. All done by hand and conventional machinery, piece by piece up mountain roads that barely existed. China learned a harsh lesson about the fragility of conventional construction methods. But beneath the Kunlun Mountain Range, nicknamed the roof of the world, lies something worth the impossible effort. The largest untapped rare earth deposits on the planet, worth an estimated $12 trillion. These minerals power everything from smartphones to electric vehicles to military technology. Neodymium for magnets, scandium for aerospace alloys, yttrium for lasers and superconductors. Whoever controls rare earth extraction controls the 21st century economy. The problem? The Kunlun Mountains sit at 15,000 feet altitude. Temperatures swing from -40 degrees Celsius to +30 degrees in a matter of hours. No road can survive here. No rail system can be built. Helicopters can't operate at these altitudes with heavy payloads, limited to only 25 tons at best. For decades, this treasure sat untouched because no machine on Earth could reach it. Until now, the world has tried to solve the impossible terrain problem before, and every attempt has failed. Conventional cranes and excavators hit their limits fast. The largest mobile crane ever built still requires 3 weeks of assembly time and perfectly flat ground that simply doesn't exist in mountain ranges. It cannot move while lifting or generate its own power. Modular construction was tested across Central Asia during the Belt and Road Initiative, but pieces don't align properly in high winds. Unstable ground shifts between delivery and assembly. Entire projects worth hundreds of millions had to be abandoned. Tunnel boring machines seemed promising until machines designed for uniform rock got permanently stuck in mixed ground. The Seattle Bertha disaster became a cautionary tale, trapped underground for 2 years at nearly $1 billion in losses. Helicopter lifting faces, physics limitations, maximum payload 25 tons. Mega infrastructure requires moving thousands of tons daily. Every solution required the environment to adapt to the machine. None could move while carrying heavy payloads. None could generate their own power at scale. China's engineers realized they needed something revolutionary, a machine that could walk directly to resources, extract them, process them, and walk back out. No roads, no rails, no traditional infrastructure required. They called it Qilin, after the mythical Chinese beast said to appear before the arrival of a great leader. The creature from legend was said to walk so gently it wouldn't disturb a single blade of grass. The engineers aimed for something similar, a massive machine that could cross unstable terrain without sinking, and the specifications alone sound like science fiction. Weight: 52,000 metric tons fully loaded. To put that in perspective, that's heavier than 400 blue whales combined. It's roughly equivalent to the weight of 100 fully loaded Boeing 747 aircraft. Dimensions: 280 meters long, 95 meters wide, and 75 meters tall, almost as tall as the Statue of Liberty. The footprint covers more area than 3 football fields combined. But here's where it gets truly mind-blowing. This massive structure doesn't roll on wheels or tracks. It walks on 124 hydraulic legs arranged in a coordinated grid pattern. Each leg can independently lift 800 tons. The hydraulic cylinders use a specialized silicone-based fluid that remains viscous across a temperature range of 100 degrees. The walking speed while carrying full payload reaches 200 meters per hour. That might sound slow, but German engineering assessments that were leaked to international media called this impossibly fast for a structure of this mass. Traditional heavy equipment of this weight cannot move at all without disassembling. Dr. Chen Minghua, one of the lead engineers on the project, spent 11 years developing the leg synchronization system. His background includes work on offshore oil platforms and earthquake-resistant buildings. In an interview with Chinese state media, he explained that the secret lies in what they call distributed pressure algorithms. Instead of concentrating weight at single points like traditional vehicles, Qilin spreads its mass across dozens of contact points that constantly adjust based on terrain feedback. The artificial intelligence controlling the legs receives data from over 2,000 ground pressure sensors, 800 accelerometers, and real-time satellite terrain mapping. The system makes adjustments thousands of times per second. The ground pressure at any single point is actually less than a human footprint, distributed so widely that even loose sand can support the machine. Western peer reviewers from MIT and the Technical University of Munich initially called this mathematically implausible. The calculations seemed to violate intuitive physics, but then they saw it work. How do you power a walking city? Diesel engines would require constant refueling, impossible in remote mountains. A machine this size would burn through tanker trucks of fuel every hour. Solar panels couldn't generate enough energy even covering the entire surface. Battery technology isn't advanced enough to provide gigawatts of continuous power. China chose something unprecedented, the first mobile nuclear reactor ever deployed. The onboard molten salt thorium reactor generates 1.2 gigawatts continuously. That's a walking city's worth of power running 24 hours a day. To put that in perspective, 1.2 gigawatts could power approximately 1 million American homes simultaneously. That's roughly equivalent to the entire electrical consumption of a city like San Antonio or San Jose. All of that energy runs the hydraulic systems that move those 124 legs. It powers the ore processing facility that can handle over 1,000 tons of raw material daily. It supports worker housing for 300 engineers with climate control, water recycling, and life support systems. It operates the drone deployment bays with over 50 autonomous vehicles for surveying and maintenance. And it runs a three-dimensional printing factory that manufactures spare parts on demand from raw materials extracted on site. The thorium reactor design offers significant advantages over traditional uranium nuclear plants. Thorium is 3 times more abundant than uranium in Earth's crust. The molten salt design operates at atmospheric pressure, rather than the high pressures traditional reactors require, dramatically reducing the risk of catastrophic failure. The fuel cannot melt down in the traditional sense because it's already a liquid, and the waste products have much shorter radioactive half-lives, measured in decades rather than millennia. China claims the system is zero emission for carbon dioxide, though independent verification remains impossible since international journalists are banned from the construction site. What makes this reactor revolutionary isn't just the power output, it's the mobility. Nuclear engineers around the world had estimated a mobile reactor of this scale was decades away from being practical. China built one in 7 years. In March 2023, after 12 years of development and countless setbacks, the 40% scale prototype called Qilin stood ready in the Taklamakan Desert. The test site was chosen specifically for its unstable sandy terrain, the kind of ground that stops conventional heavy equipment cold. 300 engineers gathered at the observation post 2 kilometers away. Screens displayed data from thousands of sensors. Cameras captured every angle. Seismographs measured ground vibrations. The startup sequence initiated at 0400 hours local time. The reactor reached operational temperature. Power flowed through the hydraulic systems. The first leg lifted, its massive cylinder extending smoothly despite the cold desert night air. Then, the second leg. The synchronization algorithms engaged, and something remarkable happened. The massive structure began to move, not lurching, not stumbling, walking smoothly across terrain that would have trapped any conventional vehicle within meters. Qilin walked 2 kilometers in controlled desert conditions that day. The journey took just over 10 hours with planned stops for system checks. Seismographs detected each step from 30 kilometers away, registering as minor seismic events. But the machine itself remained perfectly stable. The ground pressure distribution algorithms worked exactly as designed. On unstable sandy terrain, the legs adjusted in real time, redistributing weight thousands of times per second. Lead engineer Dr. Chen reportedly wept when the test concluded successfully. After more than a decade of being told his designs violated physics, of facing skepticism from international colleagues, of watching simulations fail, and being redesigned from scratch, the walking factory had proven them all wrong. The impossible machine walked. But Qilin itself is only part of the story. A machine this revolutionary cannot operate alone. Supporting this mega machine requires infrastructure that rivals entire national projects. First, the orbital relay network. 18 dedicated satellites now orbit Earth, providing real-time terrain mapping and leg coordination data. The latency must be under 50 milliseconds for the control systems to function properly. Cost: $4.2 billion for development and launch. Without millisecond-accurate terrain data, the leg synchronization system cannot calculate proper weight distribution. Then there are the emergency rescue tunnels. At 15,000 feet altitude in the Kunlun Range, helicopters cannot effectively operate. Their rotors cannot generate sufficient lift in the thin air while carrying rescue equipment. If Qilin stops in the mountains due to mechanical failure or emergency, you cannot simply send a rescue team overland. The terrain that necessitated Qilin's invention prevents conventional rescue. Underground emergency networks are being drilled at key points along planned operational routes. These tunnels must be pressurized and climate-controlled for human survival. Cost: $7 billion per tunnel, with 8 planned along the primary route. Mobile fuel stations represent another engineering challenge entirely. Specialized drones designed to carry thorium fuel pellets must land on the machine while it's moving to resupply the reactor without stopping operations. This has never been attempted before in any industry. The drones must match the machine's speed exactly while landing on a surface, generating mini-earthquakes with every step. They must connect to fuel ports that shift position constantly. The margin for error is measured in centimeters. Every 50 kilometers along planned routes, magnetic stabilization towers rise from the mountainside. These structures generate electromagnetic fields that interact with Qilin's gyroscopic core, providing additional stability data and minor corrections during operation. In high winds or seismic activity, these towers become critical safety infrastructure. Each tower costs $800 million and requires its own dedicated power source. Total program cost: $175 billion over 12 years. That's more than the GDP of 130 countries. The workforce includes 340,000 engineers and laborers across 6 provinces. Steel consumption for this single project exceeds the total amount used in the entire Three Gorges Dam, which itself was the largest construction project in human history when completed. The path to success was not smooth. Engineers faced problems that had never been solved before, requiring innovations that didn't exist when the project began. Vibration dampening at this scale seemed impossible. Each step generates seismic waves detectable 30 kilometers away. Imagine trying to process ore with precision equipment, houseworkers who need to sleep, and operate sensitive nuclear reactor controls while creating your own earthquakes with every step. Traditional shock absorbers couldn't handle the forces involved. The solution involved revolutionary active suspension systems that predict each step's impact and counteract it milliseconds in advance. Combined with noise cancellation technology adapted from submarine engineering, nuclear safety while in motion presented unprecedented regulatory challenges. No framework existed anywhere in the world for a mobile nuclear plant. Every safety system ever designed assumed a stationary reactor on stable ground. China had to create entirely new safety protocols from scratch. The reactor must remain stable while the entire platform shifts and moves. Cooling systems must function regardless of orientation or angle. Backup containment must work even if the machine tilts dramatically during operation or emergency. Leg synchronization proved the most critical challenge of all. A delay of just 0.3 seconds between any 2 legs causes catastrophic tipping at this mass. With 124 legs, that means coordinating nearly 500 separate hydraulic systems with millisecond precision, constantly adjusting to unpredictable terrain that the sensors are mapping in real time. The artificial intelligence required more computing power than was available in any existing system, leading to the development of specialized processors just for this project. Cold weather hydraulic fluid development took 3 years alone. The fluid needed to flow freely at -40 degrees Celsius to operate in the Kunlun winter, but it couldn't become volatile near the reactor's heat, which reaches several hundred degrees in certain components. Existing industrial fluids couldn't meet both requirements simultaneously. Chinese chemists developed an entirely new compound, patenting a formula that has since attracted interest from aerospace and deep-sea drilling industries. If Qilin succeeds at full scale, the implications for humanity are staggering. Rare earth extraction costs could drop by 85%, fundamentally reshaping global technology supply chains. China would become the undisputed supplier of the minerals that power modern civilization. Economic projections suggest a GDP boost of $2 trillion over 20 years, just from reduced production costs. Direct employment would reach over 800,000 workers in manufacturing, operation, and support roles. Factory positions building replacement legs and components. Engineering jobs monitoring the AI systems. Logistics roles managing the supply chains. Indirect employment estimates reach 4 million jobs in new supply chains, from raw material suppliers to specialized training facilities. An entirely new engineering discipline called mobile megastructure engineering would emerge. Universities are already planning degree programs. The skills learned building Qilin could apply to lunar bases, floating cities, and Martian colonies. Tourism planners are already developing concepts. A Qilin viewing platform would allow visitors to watch the machine, walk from observation blimps floating at safe distances. Projections suggest 10 million visitors annually to the Walking Factory Experience Center, generating billions in tourism revenue for Western China. For resource extraction, the efficiency gains defy current models. Materials gathered in the Kunlun could reach Shanghai processing plants in 3 days instead of 3 months. Shipping costs for rare earths to global markets would drop by 60%. China's dependency on foreign shipping routes through contested waters would essentially disappear. Perhaps most remarkably, proponents claim environmental benefits that seem counterintuitive for a nuclear-powered megamachine. The thorium reactor produces no carbon emissions during operation. The machine allegedly heals its own footprints using onboard biological drones that reseed disturbed terrain with native plants. No permanent roads carved into protected wilderness. Remote regions become accessible without permanent environmental scarring. As of late 2024, the full-scale machine frame stands 65% assembled at a facility in Xinjiang province. Satellite imagery shows the scale of construction clearly visible from orbit. The legs and reactor remain under construction, with the reactor miniaturization process proving more challenging than expected. The current design is 30% heavier than originally planned, requiring adjustments to the frame's structural supports. The leg synchronization artificial intelligence required a complete redesign in early 2024, after simulations showed a catastrophic failure probability of 4% under certain terrain conditions. 4% sounds small until you consider that catastrophic failure means a 52,000-ton nuclear-powered machine collapsing in one of the most remote and pristine mountain ranges on Earth. Budget overruns have already reached $23 billion beyond original estimates. The first operational deployment, originally scheduled for 2026, has been delayed to late 2028 or beyond. Some engineering analysts privately suggest 2030 is more realistic. In early 2024, lead engineer Dr. Wei Changzhou reportedly resigned from the project. Official communications cited personal reasons. No further explanation was given. A leaked internal memo, though unverified by independent sources, reportedly stated that the team solves one problem and creates 3 more. The departure of such a senior figure raised questions in international engineering communities. An MIT engineering professor who reviewed publicly available specifications offered this assessment. The physics works on paper. The prototype proved the concept works at 40% scale. Whether it works at full scale in a mountain range at altitude and extreme temperatures, with a mobile nuclear reactor is another question entirely. But they've already achieved what we said was impossible. I wouldn't bet against them. The global response has been dramatic and divided. Nations see either unprecedented opportunity or existential threat. Pakistan and Kazakhstan have signed preliminary agreements to host Qilin operations in their mountain regions, potentially accessing mineral deposits currently deemed unreachable. Russia expressed strong interest in Arctic deployment for Siberian mining operations, where permafrost makes conventional infrastructure nearly impossible. 12 African nations are reportedly in talks for future leases that could transform their economies. Meanwhile, Western governments have responded with alarm. The Pentagon has allegedly classified Qilin as a dual-use military concern in internal reports. A machine that can cross any terrain while carrying thousands of tons has obvious military applications. India's defense minister called it an intrusion machine, waiting to happen, and increased border patrols along the Himalayan frontier. The European Union proposed sanctions on any technology transfers related to the project. Australia fears the collapse of its rare earth export market if China succeeds, potentially devastating entire mining communities. If Qilin proves fully operational, analysts predict a complete disruption of the global infrastructure and mining industry overnight. Western heavy machinery companies, including Caterpillar, Komatsu, and Liebherr, are lobbying governments for trade restrictions and technology protection measures. Some reports suggest the United States is secretly funding counter-research to develop its own mobile mega-construction capabilities. though no official programs have been announced. The United Nations has no framework for regulating mobile nuclear megastructures. They simply didn't exist when international regulations were written. Emergency sessions have been demanded to address what diplomats call an unprecedented development with implications for sovereignty, environmental protection, and nuclear non-proliferation. Will Qilin walk across the Kunlun Mountains in 2028, rewriting what humanity thought was possible? Or will the challenges of mobile nuclear power, extreme altitude operations, and leg synchronization at full scale prove insurmountable? China says this machine will change civilization. The prototype already proved that walking megafactories can exist. The physics works. The mathematics has been validated. The question is no longer whether such a machine is possible. The question is whether humans can scale it to transform the world. What we're witnessing might be the birth of an entirely new era of construction. Imagine disaster zones receiving mobile factories within weeks instead of years, producing supplies and shelter on site. Imagine remote communities gaining infrastructure without permanent environmental damage. Imagine the concept of permanent roads and railways becoming obsolete for resource extraction. Imagine these machines eventually walking on the moon or Mars. So what do you think? Has China rewritten the engineering rulebook, or are the challenges still too massive? Is this the future of human construction, or the most expensive experiment ever attempted? Drop your thoughts in the comments below. And if this story amazed you, smash that subscribe button and hit the notification bell. Because next week, we're covering another engineering mega project that's reshaping our planet in ways you won't believe.